Just a notice that, and then for the people who arrive late, to just spread the word. We will take the picture, the group picture, during the coffee break this morning. So, just so that you know, before going to coffee, we have the picture.
You have a hairbrush?
Yes, you have to.
Okay, so today we have the second lecture of Michele Doro, who will talk about fundamental physics. It will be the whole morning. He has 2 lectures today in the morning. Okay, so ask lots of questions.
So we'll take it as low as possible. Right on time. Okay, so the aim of this morning is to present what are the fundamental physics searches that can be done with gamma rays. There are a lot of them. To this first part, this first half an hour, we will talk about dark matter, and after the coffee break, we'll try to cover other topics, okay? So, that's the title, and I found a way to communicate this, which I hope can help us a little in ease the topic, which is to try to have a lunch with Fritz Zwicky about the fundamental physics topic. Why is that? I don't know if you know about him. Fritz Zwicky, in the past century, was a Swiss astronomer, and he also worked at Caltech. But is considered even if this is not totally accurate, is considered the one that, say, discovered dark matter, or the one that first used the word dark matter, in German, Dunkel Materie, okay? This is his picture, but is most known not by this nice face, but by this face. He was a picky guy. He was quite aggressive with students. And he also was critical of himself and the astronomers. This is what he thought about astronomers. They are spherical bastards. No matter how look you them, in any direction, they are just bastards. So this is what it is. And he was also proud of him, like, I have a good idea every 2 years, give me a topic, I will give you the idea, okay? And it's true, he did a lot of things, a lot of new ideas. Back then, you could throw out many ideas, not caring too much if they were true or false. But what about dark matter? Well, so before entering into this, there is a review that we did together with Miguel Ángel Sánchez Conde, if you know him, and Moritz Hutten, who is not in science anymore, that went into this a book which contains a lot of information about the science that we are doing with gamma rays, besides fundamental physics. So if you want to check it further, there is the book, and there is the chapter of this book is online. So you can have more references there. Of course, today I cannot tell you that much. And I want to mention also my colleagues. This is not just my work. To do the things that we discussed today, there are several names here. Francesco Saturni, Gonzalo Rodriguez, Javier Coronado from everywhere in the world. So if you know those guys, you can get in contact with them for the topics. So, there is a delay. So I want to start first by discussing why, in general, gamma rays are good probes for fundamental physics. And are probes in a way that, in some cases, that are even better suited than what can be done at CERN, okay, for reasons that we will discuss. So, you know, new physics, you never know where new physics is, but gamma rays from space are good probes to look for this. There are a few reasons for this that I will go through. Well, the first we saw yesterday, that we have the cosmic ray spectrum, and you remember, this goes from, okay, moderate energy, GeV, but up to super high energies, which is much larger than what can be achieved at LHC, any time in the future. So there are particles that we receive from space, of course, less and less, but with really energetics that we will never achieve in the Earth, okay? So we have this engine, okay, about cosmic rays, and we saw yesterday that they power up gamma rays. We have immense energy budget. We heard from gamma ray burst, amount of energy that will never be reached at Earth or in the sun. And we have several acceleration mechanisms which can even last, they don't care, the universe, it can accelerate particles for thousands of years, what we cannot do at Earth. The second reason is that we have, okay, the cosmic rays, they are brought by injection through gravity, okay? Gravity is for free and gives you the ability to create a lot of capture, okay, increased cross-section. Again, you have the energy budget, and you have efficient energy convention, so you can produce high-energy particle very efficiently. Okay, just to give you an idea, this I brought from Ghisellini, Gabriele, who is an Italian scientist. If you compute the energy conversion by this simple efficiency factor, for example, from a windmill, okay, you take the velocity of the wind, you take the mass of the air there, and you have an efficiency which is 10 to the minus 15. From water plants, it goes to 10 to the minus 14 by using potential energy. No, cells, 10 to the minus 10 by using the amount of energy that you have there. And then you have fission and fusion, 10 to the minus 4. And in space, we have black holes, which can convert up to 10% of the mass into directly energy, okay? So a lot of potential there. A third argument is that we have a huge, what we call fiducial volume, no? You know, in experiments, we have signals from the cosmic microwave background, so many years ago. The signal that we receive at Earth can be direct, okay, or it passes through the universe, okay? So it can traces the history of the universe. And there are several places in which you have these beam dumps in which you can actually make particle interact, okay? We saw them yesterday. Again, this plot from yesterday. You have the accelerated particle here, and these B field or photon fields or gas fields are your beam dumps in which you can have particle interaction. And there are a lot of them around astrophysical object. Finally, we have something that it's not that easy to do in the Earth. We can have time of flight because we can measure the time from the photon to get to the Earth. The astrophysical event, they have time variability, so we can have things that varies in time, which we can then see how we see them at the Earth. And so we can take trace particle interaction from similar targets at different times. So we can see somewhat the high energy physics in different times in its evolution in the universe, okay? And check then the universe, how it's different and was different from now, which for fundamental physics it's important because when we look at high energy, we are also looking back in the time of the universe, okay? And finally, we saw yesterday that now we have, and you more than myself, we have this plethora of messengers, the neutral ones, gamma ray neutrinos, the gravitational waves, which are straight, so you can do astronomy with this because they trace back where they belong. And then you have the charged cosmic rays, which are deflected by a magnetic field, okay? Altogether, this makes up the new multi-messenger astronomy, which is still in its infancies, which for you, it's a good news. Okay, so our kitchen tools for today are mostly, I will not talk about everything that can be done in fundamental physics in space because it's too much. I will again focus on the instruments that we are interested more, which is ICTs and the shower front detectors, okay? I will use often the word SWGO for shower front detector because it will be the most important instrument in this field in South America. Okay, so this is our kitchen tools, the tanks, look, and the pans for the telescopes. Okay, so what are the pros and cons of these techniques? Okay. We said already, these instruments are sensitive to energies unachievable at accelerator, okay? We have multiple targets in the sky to look for the same things. We have time-varying sources. We have multiple phenomena at the emission. We have long distances, we will see, that can amplify small signals. New physics is always small, but if you have long distances and long times, you can try to amplify this effect, okay? And we have pretty good performance, 10% energy resolution, which is fine. We can check nanosecond time evolution. And the SWIGO and the shower front detector, as FT stands for shower front detector, they have a wide field of view that will be looking at the entire sky, so they are there to listen if something happens, okay? These are the pros. The cons is that IACTs, these ones, you remember from yesterday, doesn't have as a large field of view, only a few degrees, so you have to know where to point. And there is a lot of data, okay? There is a lot of data, so you need to be good in analyzing data, and sometimes for the topics that will be discussed today, if you don't do a proper analysis, you risk to miss it. The standard analysis is astrophysical sources in gamma ray experiment. To look for fundamental physics, sometimes you have to make specific analysis pipelines. And you will see that they are pretty complex sometimes. So the issue is that, you remember from yesterday, we have primary gamma rays, and we have also cosmic rays entering into the atmosphere. You remember they are much more, 1,000 to 1 roughly, but we reject most of them. We remember that we made a selection based on the analysis, for example, for IACTs, but even for shower front detectors, from the shape of the image. And we throw out more than we actually don't write into the data, 99% of those guys. So we may have a classification problem because our classification from yesterday is based on a standard pipeline which tells that this is an ellipse, so you prepare the event, you make your classification, you remember from yesterday maybe, and you say, okay, it's a gamma or a proton, okay? But sometimes when we want to do fundamental physics, this classification is too narrow, okay? And you have to do it more. So it's possible, but it can be also an advantage that there is fundamental physics already in our data, which is in the background event, not in the gamma directly event, but in the background event. So if you take magic, for example, even if we discard a lot of them, we still have saved on data, on disk, 12 billion events, sorry, okay? And some of them could hide fundamental physics. So if we give access to the data, it's possible that smart searches look for peculiar things there. Okay, so I will argue that maybe not everything about background is trash, and there can be new physics somewhere. Okay, so the menu of this lecture is dark matter now. Okay, then after the coffee break, we will talk quickly about something more, which is actual-like particle searches, magnetic monopoles, primordial black hole, and maybe LIV, okay? This is not the end. You can do other fundamental physics topic, quark nuggets, Hubble constant, other dark matter cases, tau neutrinos, if you think it's fundamental physics, heavier nuclei searches, etc. Okay? That would be really too much. We would not stay well. But again, I told you, most of these things are written there if you want to have more details. Okay, so dark matter. Let's start with dark matter. We start like that with a disclaimer, okay? What I will do today is to talk about particle dark matter, okay? So really a new particle. And why is that? Because there is an alternative theory for dark matter, which is called, there are two families. One is modified gravity, in which basically, from what I know, you can do some things by changing just the R² dependence from the distance of gravity by some function of the energy. And you have modified now Newtonian dynamics. And they were born because we will see dark matter particles sometimes fails on small scales, okay? However, in my opinions, the cosmological evidences that we will show you and the Ballet cluster put seriously MOND shafts into stress, okay? And the stress is so large that you can find online what is called dark matter debate, which is actually a fight between White and Krupa, which is nice here because they argue a lot about, oh, you're wrong, you're wrong, you're wrong. Okay, so it's funny. This is a little old. And this is, if you want to have a look about MOND, one of the more recent, this is one of the most famous guy for MOND and one of the most recent paper discussing these modified theories. For references, there are these two books that I can recommend. This one is Focused on Dark Matter, Particle Dark Matter by Stefano Profumo. And this one is Particle Cosmology and Astrophysics, very recent, by Dan Hooper, which is more focused on fundamental physics than, say, cosmology in general. It's very deep, and I like the way he describes things. It's very tutorial, as it's Dan Hooper normally. There are Excel reviews, so shorter papers like that. This one is about dark matter candidates, which I will not talk that much. And this one is the historical big book, Particle Dark Matter Evidence Candidate from like 15 years ago by Gianfranco Bertone. There is a nice history of dark matter, okay, if you want to work in the field, which really Bertone and Dan Hooper, they really went into the history and checked things until the end of the 18th century to claim that Zwicky is not the first one that spoke about dark matter. It's very interesting lecture, okay, a reading. There are dedicated school for dark matter, which is this one. So because I say this because today I will not cover it. It's really too much for one and a half hour, okay? So you have your references. And there is this new Bible written in 2024 by Marco Cirelli, which I mentioned yesterday, which is an incredible paper, not even published, but just put online, about 700 pages, in which he review every experimental results about dark matter is there. I don't know how the guy did this, okay? But here you have all that you need to study more dark matter if you're interested. Okay, so if we assume that the dark matter is a particle, as for every particle, we have, let's say, 3 ways, no, to look for a particle. So this symbol is chi. It stands for dark matter. Okay, something happens, and then you have standard model particles. Okay, it was summarized as break it, shake it, make it. Okay, you can make dark matter. Okay, for example, at accelerator by making 2 standard model particles interact, and maybe there is a channel for which dark matter can be created, if you have sufficient energy, of course. You do this, as you do always in accelerator, by not observing the dark matter and finding missing transverse energy, okay? So you can make dark matter in this direction. You can shake it, okay? So, for example, you take some standard model material, okay? For example, germanium, and then you wait for the dark matter particle from space hitting your particle and generating some events like scatterings, heat waves, photons, okay? The usual interaction. And then you have to go to underground laboratories, cryostats, and all these kind of things. This is called direct detection, okay? So you measure the energy deposits of dark matter in the detector. I will not have time to go into this technique, but while this is hard to achieve because of energy levels, there are a lot of experiments doing direct detection everywhere in the world. We're talking about 20 or about experiments in the world. What we will do today is to focus instead on the way to break dark matter, in the sense that if we start from the top and go to the bottom, we may have interaction among dark matter particles, okay? For example, annihilation or decay. And if nature is nice enough with us, the interaction can provide to us standard model particles, which we can detect. Okay, so we will not see directly the dark matter interaction, but we will see the product of annihilation or decay. Okay, so I will focus just on this topic here. So before entering, we had to enter slowly a little bit this topic. I want to start with the dark matter evidences first, to put out some dark matter facts, and then focus on IACT and shower from detector observation. Okay, interrupt me anytime because this will be a lecture full of information. Okay, so here it's Zwicky. Okay, how this all started? Okay. So Zwicky, we are in the 30s. There were optical telescopes, and he was looking at a cluster of galaxies in the 30s. And even back then, they could use the velocity of object by the Doppler delay. Okay. So if you have a gas, which is a gas of stars, if you want, which is in in virial state, so it's in equilibrium. The orbits, the average velocity, okay, this is the virial theorem, the average velocity, kinetic energy should be roughly half of the internal energy which is given by the gravitation attraction, okay? So it's a well-known theorem for this. So he applied this to, so if you substitute to U the gravitational potential and to K the kinetic energy, you obtain this simple relation between the average velocity, the mass of the halo, the radius of the halo, and G, the gravitational constant. So Zwicky observed the coma cluster first, and then other cluster, assuming a certain number of galaxies, 800 there, and by the number of the galaxies and the light, he assumed 10 to the 9 solar masses. He computed the mass traced by light, which was done back then, in a sphere of 10 to the 6 light year. And if you put the number there, you would obtain velocity of about 80 kilometers per second. Okay, but then the velocity that you observe with the Doppler factor were much larger. Okay, he was observing velocities up to 1,000 kilometers per second in the outer skirts of the coma cluster. Okay. So you have your cluster, okay, and you expect some sort of average velocity here, but instead of 80 kilometers per second, and instead what you observe was a lot larger, okay, kilometer per second of this guy. Why they are moving that fast if there is only the matter that we expect from light? Where is the missing matter, okay? That's why he started to call it, and he defined this. If this would be confirmed, we would get the surprising results that dark matter is present in much greater amount than luminous matter. Okay, he called that dark matter, but of course it didn't mean the dark matter that we mean now. At the beginning of this, people started to look. Okay, it's not new particle, but it's maybe in the form of cool or cold star, macroscopic and microscopic solid body and gases. The first guess is the standard guess. Okay, so people in the 30s of the past century thinking, okay, we are not seeing all the matter that is there. And that's why from the 30s, it took some time to advance on this part of science and together with new technology. So the next important step in dark matter came in the 60s, okay, by this woman called Vera Cooper-Rubin, which now names the SST telescope. Okay, so instead of just looking at galaxy cluster, Vera Rubin and colleagues, they were looking now at stars in galaxies, okay? And using the fact, the trajectory, the stable trajectory of an object must have a certain centripetal acceleration, which is provided by the gravity, okay? So this is centripetal acceleration, this is the gravity force, and then you compute again the similar reaction as before. Now you have a velocity, the average velocity in function of the radius is the square root of g, the mass within within that radius. The average velocity, the velocity here depends on the mass within this this range. And if you compute this, what on a galaxy, what you would expect is the following. So this is where most of the stars are. Okay. So at a certain point, M enclosed within R here reach this maximum. Okay. Here now there are few stars, too few ones. So here you should have a peak by this formula, and then a decrease. Okay, because you don't have matter anymore. Okay, you just increase this factor here. So this is what she and everybody would expect if the light, the matter traces the light. But instead, all observation were seeing something like that. This is velocity, no? This relation here, the velocity was increasing, of course, and then kind of stabilizing there. Okay, so flat. So you cannot explain this by this formula. Something is missing again. So what Vera Rubin did, together with actually a PhD, making most of the observation, Bosma, was making systematic studies. And you see on many galaxies, these are rotation curves for 25 galaxies, I just put 6. You see they all flatten, all flatten here, okay? So this observation, which is in contrast with the fact that you have just matter where light is, was seen in several objects. Now this is much stronger signature than what Zwicky did, okay? So to explain this part here, if you compute this, no, you must have more matter around the star, the optical galaxy, around here, okay? Even up to here, which you don't see by stars. So what we do, what we use as a number here to compute this amount of dark matter is what we call mass to light ratio. Why mass to light? No, because we have a mass which we infer from light, the amount of light, and the mass which we infer from dynamics. And we do this mass to light ratio by normally using the sun. So the sun has a mass to light ratio of 1 in some units, and normally stars, they have something below 5, okay? And by the Bosma observation and Vera Kupin and the rest, we see that we have objects in which the mass to light ratio is 100 or 1,000 times larger than what we have for normal stars, okay? So much more. By the same motion of stars in the galaxies, we can compute the local dark matter density. We are in our galaxy, we see stars moving, and we can check the velocity of the solar system around the center of the galaxies. And by using this, now we can compute that we have roughly a density, which is 0.3, 0.4 GeV per centimeter cube. Okay, something like a little less than a proton per centimeters cube. If you compute this value on the Earth, it means that we have something about half a kilo of dark matter in the Earth. Not that much, but still is enough to do what we will see later. Okay, so we have more matter somewhere obscure, and it is spread larger than the visible galaxy. So the general idea is this one. This is a galaxy, okay? The luminous matter ends here. And this is a halo of dark matter which is spread much more, okay? And this is the one that explains the flattening of the curve that I told you before, okay? At the beginning, all of this, say, okay, it's a sphere, I can compute like it was, well, you can compute by the potential force, how the density would change in function of the matter. You would follow this rule. It's derived from the previous equation. And then you can compute out of this, which is basically 1 r to the minus 2. So it's not homogeneous density, but it decreases. And if you use this and you integrate, you compute the mass of the halo, okay, and you compute the density over the radius, out of the outer halo, you see that you have a halo which is roughly 100 kiloparsec. So if it's 20 kiloparsec, our galaxies, the halo of dark matter has a radius of 5 times more. So much bigger than the galaxy, okay? Now, if you do a simple model, you don't know what dark matter is. So density of dark matter and interaction is not known. If you do just, let's say, a gas of dark matter, at the end, you will have infinite mass if you extend this to infinite energy. And it's not very easy from first principle to say what is the dark matter profile, okay, in general. So the dark matter profile is not studied, say, analytically, but what was done during the past 40 years was the following, was to do n-body simulation. N-body simulation means that you take a computer first, big one, and this is, for example, Redshift 10. You put at the beginning, this is not the beginning of the simulation, but at the beginning you make a grid, okay? A grid of particles like this, and then you say, okay, each particle has a certain mass, and then this is the distance among all particles. Then the grid, you have to make them fluctuate a little bit to simulate the initial inhomogeneity. And what is complex is that to understand how this moves, you have to compute, you know, the three-body problem. This is n-body problem. You have to compute that the motion of this is due to all the other rest, and this for everybody. So there are ways that I don't know in which they solved how to do this n-body simulation with grids, with blocks. It's a whole field of physics. But even like that, they get successful results. I will show you. But just to tell you how far we are from generating a universe, the minimum mass of this particle is 10 to the 4, 10 to the 6 solar masses, okay? So we are simulating, we have to reduce the complexity of this, and each particle is very big. And also, it's complex to have only dark matter or dark matter plus baryons, because baryons, they lose energy, it's much more complex physics, so they have to make simplification, but the results are astonishing for me. And then you let evolve the system from Redshift 10, 3, 2, 0, 8, and to now, okay? 40 parsec, which is little more than a galaxy. Okay, what you see, you obtain a main halo, okay, which is all dark matter, and this is by simulation. You also obtain subhalos, these hot spots. This is not light, this is not stars, this is just dark matter clumps. And then you obtain some filaments that connects the galaxies, okay? Cirelli, I told you, the one that made the Bible, collected all the simulations, and you can find in Cirelli all the simulation and all the description of the simulation if you want to have a look. It's a full field of physics. And they also provide what's relevant for us, sorry. Once you have the image done, you can compute the mass in function of the distance from the center, the number of objects in function of the distance, the number of objects in function of the mass, and all these things that tell you what you would expect as dark matter everywhere in the universe, okay? Which is relevant because this we don't see, so we have to simulate it. So let me show you here n-body simulation for three models. You start from the same things, but you can, when you make it evolve, okay, so you have to see these three in columns. What you can choose from the, besides the mass, is how this particle interact in the sense of what is called the streaming length, okay? More streaming length means that the particle can interact less and then they can move faster, okay? They can move more. If you have a short interaction length, you start to clamp more. So you would see from here that this is a simulation with very large free streaming length, okay? This is with medium free streaming length, and this is with the short free streaming length. You see that they are different, okay? So this is the result of the simulation. Now you compare with actual observation, okay? These are catalogs of galaxies in the universe. You are here and we are counting the number of galaxies in the universe, okay? This is the same. So take this image. For you, this resemble more this, or this? The right one, okay? The right one, exactly, is correct. You see the number of filaments. The right one is what we call cold dark matter, means very small free streaming length, because it's cold, okay? It doesn't have a strong velocity, and is the paradigm now. So this is what is called warm dark matter. This is what is called hot dark matter. You can translate this also to mass. Cold dark matter is around the GeV, warm dark matter is around the keV, and this is what you would have, for example, if you have EV, like neutrinos, dark matter. So we expect that cold dark matter is the particle as a small free streaming length because of n-body simulation and comparison with galaxy count, and not only. This is one of the, so these n-body simulation are really good already. Okay, also out of this, don't look too much into the formulas now, because we are simulating everything, what we can do is to compute the density profile, the shape of the halo. So look here, not above. This is the distance from the center of the halo, okay, in kiloparsec, and this is the density in function of the distance. So you see that we can have, these are Caspi profile because they are Caspian in the center. What does this mean? That I have a lot of dark matter close to the center, and then it decreases very much here. Here, these are two instead called chord profiles because they are flat, okay? They are flat and then they decrease. So this means clumpy profile, most of the dark matter is here. Chord profile, it's more spread and then it decreases out, okay? And what is the result is that n-body simulation prefers clumpy profiles, while we will see some observation prefer the Caspi, the flat, the core profile, sorry, okay, preferred by observation. And these are simply the function describing this, okay? Don't need to read them now. What's nice now, and I will use this many times in the presentation, is that there are a lot, you don't have to write this in your computer and make mistakes. Some people before you made mistakes and fixed it, and everything is now, for example, in gamma pi. You take gamma pi, you can generate whatever profile you want and do your simulation, okay? So everything is open source, so it's much better now. Okay, so we have first this n-body simulation that tell us what we expect as dark matter just by giving a particle mass and an interaction length. Then, what is? We still haven't said what can be dark matter, okay? So there is a nice plot by, well, this one that describes the particle physics that we know. We have the quarks with the gluons, the strong force. We have the electrons and the neutrinos. We have standard matter, unstable matter, force carrier, everything within this rectangle here, even with the Higgs is what we know about particle physics. There can be something outside the standard model. We have to look for particles outside the standard model because all the particles here, especially the neutrinos, cannot be dark matter because they are too light, okay, for dark matter. They are not cold dark matter, so they are excluded already. So if we want dark matter as a cold dark matter, we have to invent a new particle. There's no way out. Okay, of course, having a new particle, you have to convince our guests that we have a new particle. So you need to have strong evidences for this, and I will show you that gamma rays can provide that. Okay, so something new. What can be new? Okay, now don't be scared. This is a plot that Tim Tite from the US did about the models of dark matter. Okay, very complex. There are many, many theories of dark matter. And I cannot even go into the detail of this. There are supersymmetry, extra dimension, little x, QCD axion, sterile neutrinos, etc., dark photons. In the web, in the archive, there are so many papers around, about dark matter candidates that it's impossible to read. So it's a problem now because we don't know how to look for these guys. And what's nice for us is that many of these guys, they produce gamma rays during the interaction, okay? So we can group the family of dark matter particles into 3 regions, okay? But look, it's very wide. So all particles in this range are viable models that can explain dark matter. The issue is that they go from 10 to the minus 22 electron volt to the mass of the sun and larger, okay? So we are so good in saying what is dark matter that we have, I don't know, 40, 50 orders of magnitude of possibilities. The 3 families that we will discuss today are basically the WIMP, okay, which is the standard prototype for cold dark matter, which can annihilate or decay in space around the TeV. WIN stands for weakly interactive massive particle, okay, which I will spend this morning. And then in the second part of the lecture, we can explain about axions, okay, which are ultralight, which can leave imprint on gamma ray spectra after the coffee break, and primordial black holes, okay? All these 3 can make at least part, these 2 guys here can make at least part of the dark matter, okay? But you see, we are facing a large part of unknowns, okay, in the possibility. Okay, what's nice is that above here, accelerator cannot really say much. Okay, let's start then with this model here, which is nicely described as an example in terms of supersymmetry. It's a very criticized theory now, but 20 years ago when I started this, it was the first candidate to look for it, okay? An example, I show you this an example how you can make a dark matter particle, invent one. We saw the standard model particles here, okay? And we know that in this model there are some problems, and one, for example, is the scale difference between the forces, okay? So there is a way to fix this problem of particle physics, which is to invent a supersymmetry. Why supersymmetry? Because for each particle, okay, you have a partner which is symmetrical, okay? You see that for everybody you have a quark, a lepton, and SUSY force carriers, which has this tilde, okay? Now, as it happens for, of course, the symmetry is broken at our energy, but if you go to the early universe, there is a symmetry between these 2. And as it happens to our universe, you know that these are not stable, and we only have these 4 guys as stable ones, okay? The same happened here, okay? The lightest of this particle can constitute stable state, okay? What does it mean? They are stable, they were produced in the early universe when there was equilibrium. Then at a certain point, most of the matter, they could not interact, the supersymmetrical partner, with the standard model partner, so the lightest supersymmetrical partner was stable and remained as a relic, okay? You can imagine this. Now, there was no SUSY interaction between them, so we have a relic which is constituted by the lightest of this particle, okay? I hope it's clear. So the lightest of the supersymmetrical partner is not uniquely defined, depends a little bit on the model that you do, but one of the most famous one is called the neutralino, okay, which is a mixture of Wino, Bino, Xeno, and all the force carrier, okay, fancy names. The important thing is that you can generate LSP, lightest supersymmetric particle, in several ways. This would be a relic of the early universe and could be a dark matter particle there, which do not interact directly with standard model particle anymore, okay? So what happened with this particle in the universe, okay? If you are in the early universe, there could have been a moment in which there was an equilibrium with this particle and the surrounding plasma, okay? So you have interaction, and then you have production, which depends on the cross-section. between your standard model particle and the plasma, if you want, sorry, not standard model particles, and the dark matter. So dark matter is produced, annihilate, generate other particles, and vice versa. There is sufficient energy for that. Now, if you think the universe expands and then the temperature goes down, what happens first, okay? One particle is heavier, okay? The other are lighter. One cannot be, the balance is, as if with every other particle, is not in equilibrium anymore. So you only have not sufficient energy to generate dark matter particle anymore. So the number, the amount of dark matter stays the same, and this is what is called chemical decoupling, okay? So how, here you have, this is the Comoving number density, I hope you know this plot. This is the density when you have thermal equilibrium, and here is when you cannot produce dark matter anymore, so you just decrease a little bit, and it's a comoving density. After this, what happens is that the universe expands so much that even the annihilation, so the interaction between dark matter and dark matter, is not efficient anymore. So you don't have annihilation, and the annihilation stops. It's what is called freeze out. This means that the density is constant. Up to a certain point, okay, you have dark matter, there is not enough energy for this particle to do anything because it cannot even annihilate because the universe is too cold, okay, with respect to its density. And out of this time or moment in the universe, the amount of dark matter is kind of fixed. You have imagined that you have particles everywhere, okay, but they cannot do much. What happens next, of course, we will see, is that they start to attract one another because they have mass, okay. What happens with the WIMP is that if you compute, okay, all this equation with the thermal equilibrium and all the other particles, at the end of the day, you get a density, you know, the ratio with respect to the critical density of dark matter, which is a complex formula, depends on the number of degrees of freedom, the time when this happens, but we have a value of cross-section which can explain the amount of dark matter now, which is called thermal, because there was thermal equilibrium, which is 10 to the roughly 2 times 10 to the minus 26 centimeter cube per second, okay? Is thermal cross-section times velocity, I have to say that, which is a number that I will use. So out of basic principle of cosmology, and assuming a certain time, we have something that will tell us how strong should be the interaction strength of dark matter. Okay, so what happens next? We have dark matter particles, which we cannot really see in the universe, but the first thing that we can see with light is actually the cosmic microwave background, no? I assume you know what I'm talking about here. So the cosmic microwave background, something about 400,000 years after the Big Bang, and you have to think what would happen if I add dark matter, no? Here is an imprint of the particles that were in the universe before, and they would leave these anisotropies here. So you have to think what would be if there is dark matter and if there is not dark matter. And actually, you see that during this recombination, if you have a lot of dark matter, so a particle with the energy, they can ionize a lot of the atoms around, okay, of the hydrogen in the universe. So you will clearly see an effect here, because instead of having recombination, you would have much less recombination if you have too much dark matter or too little dark matter. So this is studied by the anisotropies of this, okay? I assume that this is known a little bit. This is the way we study the power spectrum of the anisotropies in the universe, if you've taken a cosmology course. And then you have the power of this multiple number here, the power spectrum of the anisotropies. And what happened is that, for example, just having a zoom at the first angular scale of these anisotropies, this is what we see, okay, by the anisotropies. If there would not have been dark matter, there would have been much less anisotropy because of this ionization effect of the dark matter, okay? So there is a very strong imprint here that there is something beyond the baryons that we know in order to be able to see the level of anisotropy that we see there. if there were not dark matter, this would be kind of washed out, okay, like with the acrylics colors, okay? So we have this, we see these dots because there is a lot of dark matter there. And for me, this cannot be explained, or for everybody, this cannot be explained with Mond theories, okay? So must be particle. Okay, so we have a very strong signature of particle dark matter from the cosmology, okay? So this is the dark matter that would be around that time. So most of the universe would be made of the energy in the universe in dark matter, and then photons, neutrino, and baryonic matter. You let the universe evolve, and this is what you have now, in which this fraction is maintained a little bit, but now you know that we have this dark energy contribution. But let's focus here. If you have that much dark matter with respect to standard baryonic matter, what happens? If you let it evolve, dark matter start to attract, okay? And then dark matter must have led structure formation. So this was an Bari simulation, so this is just dark matter, but you may expect that here is where a galaxy later on formed, and here and here and here, which is what we see in optical light. So dark matter driven structure formation. Okay, the other evidence for me that dark matter is a particle is what is called the Ballet cluster, in which we see two galaxies cluster interacting and passing through, okay? And these are false color, but you see that the blue traces the red traces the gas, which is slowed down by the crossing, and the blue traces the gravity, okay? So it's clear now the gas is slowed down because of this friction effect, but the dark matter, it's collisionless, so it can cross one another without interacting that much. Okay, and by seeing this, you say, okay, oh, look, these two clusters, they just pass by, and only the gas slowed down. So they didn't disrupt, so most of the matter must be in particles there. You cannot explain this by Mond. This evidence is not just one cluster, it's 72 and with a large significance. So this is true for the moment. And again, it cannot be explained by modified theories of gravity, okay? This is just two or few evidences. I put here more in a slide from Miguel Angel. But you see that we have evidences of gravitational imbalance from galactic scale. We saw them, galaxy cluster scale, and from cosmological probe. So we expect to have a new particle. It's just we don't know exactly where it is. So gamma rays, I think I need to rush a little bit. 1 hour already? Wow. Okay, I need to be quicker. So why gamma rays are important? We have theories of dark matter, but at the end, okay, in any of these, if you take most of these particles and you make them interact, okay, not only the supersymmetric neutralinos, you have free energy, and as every time with annihilation, you may have quark, leptons, boson at the end, okay? And after all of these processes, you may have and found gamma rays, okay? Because it's normally produced in a high energy interaction. You have annihilation, you can have decay processes. Now, what is interesting about doing this with gamma rays is that this is what is called a gamma ray spectrum. So this is energy, okay? And this is the number of photons, gamma ray photons, that comes after this annihilation. And you see that this is one example, this is another example, this is another example. These are spectra, okay? And they are peculiar in what sense? There are no astrophysical objects. If you take a blazar, if you take a quasar, if you take a supernova, they will never display this kind of spectrum with sharp cutoff here and this kind of distribution there, because there are no astrophysical mechanism there that mimic this. So if you see this spectrum in the sky, good. It's identification of dark matter, okay? Not only this, because of what I told you before, there are halos, subhalos. If you see it in one place, you expect to have the same exact spectrum in other places in the sky, because dark matter is the same everywhere. So take that you observe this and you observe it multiple times. This is identification of dark matter clearly, okay? Of course, you need to know where to point the telescope or where to look for dark matter. I told you already about the peculiar spectrum, and I need to tell you that why it's so general. Normally, to compute the annihilation spectrum, I have to know exactly what particle is, which are the branching ratio to which channel, okay? But we will see that from what we do, we can simplify things by assuming, for example, benchmark model. Take, for example, annihilation of dark matter into BB bar or tau plus tau minus. BB bar is blue, tau plus tau minus is orange, okay? You see that if the matter is 500 GeV or 5 TeV, the spectrum are the same. It's very general, no? They don't change that much except from some channels. So we can take benchmark models when we do dark matter, and even if we take actual, so there is no, sorry, I want to say there is not one dark matter model that annihilates 100% of the time into BB bar. But even if we take an actual model, which is, for example, the Xeno, it's one kind of particle, this particle decays into WW, ZZ, gamma gamma, with this branching ratio, okay? What is his spectrum? Xeno is the green one. You see that the Xeno is very similar to the black, which is WW, so we can take benchmark annihilation models. So in gamma rays, we don't care so much about what is dark matter. We just look for this channel. If we see something strange, then we have detect dark matter, which is a powerful thing that accelerator and direct detection experiment cannot do that easily. So we are just looking at fancy signal in the sky. All of this is model. Again, you don't have to do everything from scratch. You can find the parameters of this by Marco Cirelli. This is his picture. In this recipe here, and you have all the files that gives you how many photons you have per annihilation. So you can read these files and don't do the microphysics again, and you have in gamma pi your at production gammas file, which you can read to give you the spectrum. Fantastic. Okay, this is an example on how you do it. So very, very, very few lines to be able to simulate a dark matter spectrum. Then, besides the spectrum, if I want to compute now the flux of dark matter, I am at the Earth, and I want to compute how much photons, gamma ray photons I have here. There are two lines. Let's start with annihilating dark matter. So you have two particles of dark matter doing something and making standard model particles, okay? This is annihilation. The amount of photons that we expect at our telescopes depends, of course, on this, which is the number of the spectrum that I showed you before, the number of photons for one annihilation. Then it depends, of course, on how much the dark matter is interacting, which also depends on the mass. Okay? This is what is called particle physics. Okay? I have to define how many photons I have per interaction, what is the interaction strength, and what is the mass. And then I need to have a factor which is called J, for historical reason, which is written like this. It's long, but it's not complex. Annihilation, J factor, is the integral, well, it's shown here. There is only an integral over the line of sight and the aperture of the square of the dark matter density. This is my dark matter candidate, okay? I want to compute how many photons I have from here. I have to take my detector and compute the solid angle in which I see dark matter. So this is the integral over the aperture, omega, and the line of sight, okay? And then I know how much dark matter particle I have there. Plus, I multiply with how many photons I have for each annihilation. Okay? And you see that this depends on the square, because for annihilation, the probability depends on, you have two particles interacting, so the annihilation depends on the square of the dark matter density, which is very relevant because we spoke about density profile, okay, rho in function of the distance, like these ones, the Caspi profile. But the fact that we have rho squares means that this density is multiplied, okay? So we expect to have signal where we have a lot of high density because there is a square factor. So we expect to see signal from the very center of the galaxy because you have to multiply this to square this factor here, and less from the outside. This is true for annihilation. For the dark matter is totally the same, except that the astrophysical factor is just the integral over the density, because dark matter is decaying. And here you don't have branching ratio into standard model particle, but just lifetime factors, okay? I will just quickly say this. How do we compute this J factor, okay? How we have this guy here. How do we know how much dark matter is there? What is done is to use, you make a Jeans equation, which is equilibrium, let's say fluid dynamics in space. You compute, you take the stars that you have there, and you model the stellar profile, plus you say, okay, there is stellar profile, which I see, plus there must be dark matter. If I put everything together, I have the amount of dark matter that I have there, okay? This is this Jeans equation here, which is complex, but you have to do a lot because you have to look at the stellar profile. These are stellar profile, intensity, look at the single stars and see the velocity distribution, select the ones that are related to your object with respect to background. So you have to do a lot of astronomical modeling, okay? And this, again, you don't have to do it yourself. You use codes like CLAMPy, which from the data that you put gives you the dark matter profile, okay? So at the end, we start with producing our density radial profile. We take a source, for example, BOOT-S1, and this is the center of the source, this is the distance from the center, and this is the density profile. We have to generate it, okay? And you see that the dark matter is this curve roughly peaked here that I showed you before, this one. Out of this, we generate the astrophysical factor, this integral that I showed you before, which this is the astrophysical factor within a certain angle. No, we have to, the object is extended, and I have to ask myself how much dark matter I have from the central part, outer part, and outer, and outer, and outer, okay? And you see that it's like that. It increases, so I have to look at this object in the sky. Okay, so where do we look now at this target? Okay, let me skip this one, I don't have time. Where do we expect to have dark matter? So this comes from embodied simulation, I told you, no? And the first thing that we expect is to have a lot of signal from the galactic center, okay? Can you guess why the galactic center is the best target? Huh? There's a black hole, but the black hole came after dark matter was concentrated there. Huh? Exactly. It's close, okay, so there is always the R² distance, but the density is much there than in other part of the galaxy. We are looking at ρ², so it's really there, okay? Fantastic, the galactic center and the surroundings. In the galaxy, now a little larger distances for us, we have globular cluster, we have dwarf galaxies that we'll talk about. Why is this? Why we're looking at galaxies? Because I told you before, dark matter, the galaxies formed where dark matter was concentrated. So if we look at where light is, we also expect to have a lot of dark matter there. But there are some cases like dark subhalos, which, what is this? It's just a clump of dark matter in which maybe it was formed outside the central part of the galaxy, so the baryons didn't collapse there. There was no galaxy formed, but still we have the dark matter clumps. So dark subhalo is just something only made of dark matter. We have other galaxies, but now we start to go far away from us, and we have galaxy clusters, okay? Plus line signal and another object. The unlucky thing is that in the galactic center, I don't know if you know, I mean, well, we expect a lot of dark matter, but there is also a lot of other things, no? There is the black hole, which drives, there are pulsar, there is a lot of gas. So this area is confused with astrophysical signal. Okay, so I will just present some results, and I will focus on CTAO also because I worked on those, and I don't have time to focus on this. So let's focus on a few targets. The galactic center, the dwarf spheroidal galaxies, then we have the Large Magellanic Cloud, and the Perseus galaxy cluster if there is time. Okay? So if you take the galactic center and you want to observe dark matter, what do you have to do with the telescope? Okay? So it's very extended, okay, the signal, and your telescope has a field of view like this. So CTA has a program, or maybe a little larger. CTA is a program to make snapshot and cover the entire area around the galactic center, okay? Here, which is this plot, all the pointings. Then you say, well, okay, let me check. I told you there is dark matter. This is the energy, the counts in function of the energy. This is what I expect. You remember the spectrum from dark matter. And these are the astrophysical background. So, which is, for example, cosmic rays, electrons, and other gamma rays. So I want to look for this signal out of this signal, okay? So I know that I will see a little bump here, and then I have to make a very careful analysis. So dark matter signal will be, anyhow, very, very dim and dimmer than other signal. You have to simulate, and again, this can be done in gamma pi. Once you have a region of the sky, you simulate all your signals for cosmic rays, diffuse background, and then dark matter models. So we want to look for this, where we know already that this is the, the background that we have, okay? So you can imagine that is difficult. Let me skip this. And let me skip also this. At the end of the day, once you observe that part, because we have our signal model, which you remember, the flux of dark matter that we have was proportional to the cross-section, the mass, the number of photons per annihilation, and the J factor, okay? If we see something, then we should see an excess. We look at the center of the galaxy. We have the astrophysical spectrum. Suppose that we see something like this. This could be dark matter, okay? Then we have detection, and because dark matter spectrum is this one, and then we go, Ulysses go to Stockholm to take the Nobel Prize. But even if you don't see anything, it's really, really relevant, because if you don't see this, you can always say, okay, the dark matter particle that would have created this signal is excluded by my data, okay? It's not there. I can only say that the signal was smaller than, for example, this one, okay? So what you do is to put upper limits, okay? So we normally put upper limits in this way, okay? We assume a spectral annihilation. We measure the J factor, the amount of dark matter, and then we have these two parameters that are reported here. So we can say that, for example, for a particle of mass 10 to the 3 GeV, 1 TeV, this is our limit. The cross-section cannot be larger than 0.7, 10 to the minus 26. So this is an upper limit, okay? This excludes all that is above this part here. And only dark matter model living in this part of the spectrum can survive, okay? So out of the galactic center, with CTA and all the instrument in gamma rays, of course, we want to try and check dark matter, but even if we don't see it, we learn a lot by excluding this parameter space. Of course, for what I told you, it's a very dim signal. It's not just one line and we go home. The limit is the same plot. The limit depends on the channels. So I have to assume BB bar, I have to assume tau plus, tau minus, etc. The limits depend on the benchmark channel that you select. And then if you start computing, if it's a Caspi profile, it's here. If it's a core profile, it's another limit. The accuracy of the limits is model dependent, okay? With new physics, you have to deal with that. You don't know where new physics is, so you have to start somewhere. Let me also skip this. I want to tell you that only quickly, again, it's the same plot. Now let's check at this. This is the galactic center. These are the limits put by Fermi telescope, okay? For dwarf, this is the CTA limits for the galactic center, and this is the SWIGO limit for the galactic center, which is expected. So, same plot. What do we learn from here? These are all upper limits. Okay, we learned that Fermi is the best in putting limits below this area here, no? Because this line is lower than this one. CTA is the best in this area here, and SWIGO is the best in that area here. We have to all work together to constrain the parameter space. And we don't know, there is no probability, we don't know where dark matter is. It could be here, so we just could have observed a little longer, or it could be here, or it could be another particle. But this is what we do. About the dwarf, which is the second target, and I will just put another one. These are, what are dwarf galaxies? They are smaller galaxies, 10 to the 8 solar masses, orbiting our Milky Way, which is the guy there, okay? There are a bunch of them, and they are gravitationally bound. They are galaxies which we see, and we expect to have dark matter there, okay? Now, if we look at these guys, okay, we can distribute them in a plot which is intensity, so light intensity in function of the, so magnitude in function of the radius of the dwarf, okay? And you see that we have two populations. One is called the Milky Way dwarf galaxies, which are a little larger and about this level of intensity. And if we look at classic globular cluster, they are here, okay? They are same intensity, but more compact. And why they are larger? Because there is dark matter there, okay? So these guys are very good candidate because they are close and they are a lot around us. There is a bunch of them which are reported here. You see all fancy names that we know, Ursa Major, Segue, Horatio, blah, 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 okay? And they are classified here in function of the J factor, the amount of dark matter, okay? You see that some are very bright and some are less bright. But you see that the galactic center intensity is much larger. We expect, if everything goes well, that the galactic center is very bright. But the dwarf are here, okay? Now, there is a problem because we have uncertainties. We don't know exactly where the dwarf are, but we know that in a few years from now, new instrument will tell us all about the dwarf, okay? All about the dwarf galaxies. We expect to see all of them. We have looked at, this is my report, and this is Houghton. We have looked everywhere in the sky for this dwarf, a bunch of them, and all of these are only upper limits, okay? So a lot of investment, but we didn't detect dark matter. I want just to tell you, now I start to using too many plots, that simply by the n-body simulation, we expect, so these solid lines are simulation. This is mass, sorry. We expect to have a lot of dwarf galaxies with larger, smaller mass, and a few with very large mass, okay? There can be, I want to tell you that we may have few, maybe one or two dwarf with very, very large mass, and then very, very large amount of dark matter, which we have not detected yet. So even if we have a lot of target here, okay, it doesn't matter to have many of them. We just need one with very large J factor there, and if we point at the right target, we may discover dark matter. So we have a candidate now in the past years, which is called Ursa Major 3, which in this plot here, it would be here, which is very small, but still intense. This would have a lot of dark matter there in this plot. And if we compare, this could be something like here, as bright as the galactic center, okay? Called UMA 3. If this is confirmed and we point the telescope there in the future, then we may have a detection of dark matter. So even null results, it depends, no? You never know if you're lucky or not in detecting the same source, the good source. Okay, let me skip this. So we have a paper under publication. It will be probably put online today, this paper, which tells us everything you want to know about the dwarf. And we checked the list of all dwarfs in the sky and computed all the details about dark matter profiles in the dwarf. We checked the signal, how it would appear in CTAO, and found our results. So let me show you this result here. Or better, maybe this one. Let's focus just on the right side because I don't have that much time. This is the usual plot, okay? Mass of dark matter and cross-section. We saw this line before. This is the Fermi limit, okay? This line here. And you see here we have a comparison of different limits from different targets in the sky from CTAO. This area here is the galactic center, okay? It's very low. Goes very low. It's the strongest one, but you know that there are a lot of uncertainties here. I told you before, the limits depends on the model. If we observe the Large Magellanic Cloud, then we would have limits here. If we observe our dwarf galaxies, then the limits are there, which is 2 orders of magnitude. So where to look at? This say, why I don't want to look at this one because it's less strong than this limit here. Fine, true, but if we discover an object like UMA-3, this very small and dense dwarf galaxies, our limit would go here, so the strongest ever, okay? So sometimes in astronomy, we have to wait for other instruments to tell us where to point our telescope. For SWGO, they will have a full sky, and so they will be more lucky in this. Okay, so let me skip the dark subhalos, which are, just to tell you, dark subhalo means only dark matter. How do you know in the sky if there is an object that is made only of dark matter? It doesn't make radio, it doesn't make X-ray, well, maybe a little bit, it doesn't make optical, okay? So you want to look at gamma, but you need to know where it is. So SWGO can tell us something, but there can be objects in the sky in which we don't know they are actually emitting gamma rays unless we point it. And you can put a limit, for example, with CTA, because after some time, you will have seen a large fraction of the sky. So maybe you can find by luck, I mean serendipity, a gamma ray emitter which you cannot say it's anything astrophysical. If it's not astrophysical, it's a good dark matter candidate. Let me also skip this one. This one, this is just a collection of the object that I told you about. Dwarf galaxies, galactic center, galactic halo. So, to conclude so that I stayed on time. Up to now, we have observed thousands of hours everywhere in the sky for dark matter, okay? And we have not seen any signature of it, okay? This is in this report here. So, do we learn anything by not seeing dark matter so far in the sky? I already anticipated it, but I would say that yes. First of all, what we are doing is complementary to the other things that are done in search for dark matter. Okay, at the end, if we want to search for dark matter, we have accelerator, production, we have scatterings, we have annihilation, okay? We are probing, but most importantly, not only we are complementary in the sense that if you make a model, this is mass and this is some interaction cross-section. If you really take real microphysics model of dark matter, and you ask yourself, will this model be detected by direct detection experiment or gamma rays? You see here, so the colors are excluded by indirect detection, but not by direct detection, this part here. Excluded by direct detection and indirect detection here, and excluded by one of the two. This part here, okay, is excluded by us, gamma rays, and not by anybody else, okay? So if you take all your model of particle physics dark matter, this part is made in a direct detection experiment, this is discovered by them, this is discovered by both experiments, but this one is only accessible to space experiment, to satellites and ground-based experiment in gamma rays. We don't know where dark matter is, but it's really kind of important for us to look at these places where we are the only one that can provide an answer, okay? So to conclude the lecture, and I apologize that I had to skip too many slides, we have incontrovertible evidences. I think that the dark matter is in the form of particles. Don't trust the colleagues that tell you it does not exist. My opinion, okay? Then, okay, you're one of them. From the astrophysical point of view, okay, we have a coherent picture so far of the astrophysical picture, and we know that we may find a super target in the future, which is maybe dark, and we can only see it in gamma rays, which is bright enough to be able to discriminate it, okay? We need a lucky strike, and it could be one of the dwarf spheroidal there. If we have a small telescope, small field of view telescope, you have to know where to point. This is a major limitation. So it's important to create synergies with the instrument that tell us where to point, okay? For you that are maybe interested, there is pipelines now to make all this analysis. They are more and more easy to use, because otherwise, I think I showed you that we have to put a lot of things to make this analysis there to compute our limit. But now everything is being done in CTAO. There will be data challenges here in which I invite you to participate, in which you have a simulated sky, you have to look for there, and maybe you can discover dark matter in a fake sky. So it's a data challenge. CTA will be organizing data analysis in which I tell you, look at this position. I don't tell you if there is dark matter or not. Try to make the analysis and try to see if you put upper limits or not. But most importantly, from the particle physics point of view, gamma rays are rather model independent, so we don't actually need to know that much about the microphysics. We just want to look for fancy astrophysical signature in the sky. And we are we have regions where we are the only one that we can probe that part of the space, okay? This is the good part. Of course, even myself, after 20 years of searches, which are reported in my review, it starts to be a little boring. So we are not seeing it, but maybe you are luckier than I have been in the past. Okay, thank you.
So any questions?
Okay, thank you. So I was wondering, just because we talked about experiments yesterday, in the 30s and in the 70s from Rubin and Zwicky, how did they measure velocities, and how did they count or try to count how many stars there were in clusters? Because they only had optical telescopes, right?
No, I think they have spectrographs in the 30s. By Doppler shift, anyhow, velocity by Doppler shift.
And how many stars in a cluster?
I don't know, but no, it's written there, hundreds of galaxies in the galaxy cluster. To make 2C stars that, well, you have to wait for the 70s and larger telescopes. But galaxies, if you see the Coma cluster, super bright, super bright. So it's one of the closest, and you can see many galaxies.
So you counted them?
You counted them, but it's hundreds of them.
Yeah, 800, I think.
Yes, something like that.
Thank you.
There was a question there.
Hi, thank you for the presentation. I I do remember that there was some excess reported for
Yes.
AMS and Pamela, but I was thinking, okay, they can measure the fluxes, but how can this be measured with ground-based detectors? Should we expect some strange signal? Because in ground-based detectors, we detect the secondaries. So how can we relate to dark matter?
So AMS, I have the picture of the excess there. So I'll show it to you. Thanks for the question, by the way. Here. So you mentioned first AMS. AMS measure charge particles, okay, and actually identify them. If you have charge particles, you don't know where they come from, okay? You just count them, but you don't know the direction. So you can, if you have annihilation of dark matter, this is something that I skipped, you have gamma rays out of these processes, but you can have electrons here, protons after the end, anti-electrons, deuteron, etc. Okay? We are looking at this, but there are a lot of instruments, including AMS, that is looking at that. The problem is that you don't know the direction, so you don't do astronomy. Now, if you see an excess, for example, you compute one latest excess was the anti-electron excess. Or take the deuteron, which is even better. You don't expect deuteron from spallation, or you expect a certain amount of deuteron from interaction of cosmic rays, which you model pretty well in the galaxy. Then you count deuterons, and you see more deuterons than that, okay? Anti-deuteron, sorry. So then you can say, well, look, this excess is due to dark matter, because my theory of cosmic rays cannot predict that part. This is what is done. There are anti-electron excess also, okay, which is measured, and you say, okay, I have my sea of cosmic rays, I estimate this number of anti-electron, and I see an excess. This is actually what was observed. What is the problem there? Is that you have an anti-electron excess, but if I put a pulsar, okay, here, you don't know where pulsars are in the center of the galaxy. If I put one close to me, then it can make the entirety of the anti-electrons, okay? So with charged particles, it's super good, especially in some channels, but the fact that you don't know the direction, complicated. With gamma rays, you're looking where you expect the dark matter. In our case, this is an example of a detection of dark matter, which is this one. This is flux, okay, and this is energy. This is from Hooper, the one that I told you before. And there are many papers about this galactic center excess. So they are looking at the galactic center, and this is the spectrum that they would expect from astrophysics, okay? And they see a hill here, okay? They see an excess, okay, which later on flattens out. And what is this excess? You can take a model of dark matter, 20 AGV, annihilated into BB bar with that sigma V, and you get this line, okay? This line here, which can explain your excess. So dark matter at the galactic center would always be seen as an excess over the astrophysical background, okay? If this is true, then you don't put upper limits. You say, okay, there are two. In this case, for example, there are two dark matter particles that can explain this. One is 10 GeV annihilating into tau plus, tau minus. One is, I don't know, 50, 60 GeV annihilating into BB bar. Which of the two, we don't know. But these are two candidates. Again, here people are arguing because we don't know if this is dark matter or a bunch of pulsars emitting, okay? So what is the issue is that the galactic center, you always have this background. If you do dwarf galaxies, this background doesn't exist because dwarf galaxies, they are not active, okay? But this is how you would see as an excess of signal with a fancy shape, which it's hard to make with astrophysics normally, okay? But at least you know where you're pointing.
Okay, one more question? I have a couple of questions too, but
For the coffee.
Oh, just from the, let's say, methodological or epistemological point of view, Michele, if we ever detect one of these smoking guns in the gamma ray, so indirectly, would it still be possible, would it be possible to claim dark matter without any counterpart of direct detection? Because from what I see, there is always some way in which we can cook some astrophysical model which is very complex, no? Always
Yeah.
to reproduce even strange spectral shapes. So do we need to have both, or the indirect could be a definite?
So in the galactic center, there will always be, very likely, another explanation. Okay, unless you model super well the Fermi bubbles. So maybe in 25 years we have that. In our case, there are parts in which we are only sensitive to dark matter, and the direct detection will never be sensitive to 1 TeV, dark matter particle, very likely. Okay, too little cross-section with matter. But you remember one of the first slides is that if I see it once in a dwarf, maybe I don't convince you, but if I see the same signal on 2 dwarfs, then it's very, very unlikely that. So because with one excess, so this is my spectrum, okay? Energy and flux. Suppose that I see something like this, okay? First of all, this tells me roughly what is the mass of the dark matter. Super important factor. The shape of this gives me roughly if it's more BB bar, WW, or leptonic channel, okay? Fine, this can have other explanation, but if I look at another source, then I build, of course, then we get a lot of money to build other telescope to stay all the time on these guys. If I observe another target with the same spectrum, then it's impossible that it is just astrophysics, because you don't have pulsar, for example, there. You don't have any stellar activity, so these gamma rays, where do they come from, okay? And then there are the dark subhalos, other topics. But in my opinion, if we see it, so this is very improbable, but if we see it, then we have a detection, identification of dark matter. Yes, exactly. So, but still, we are working in a place in which we are the only one that have sensitivity there, so especially Swigo and Lasso.
okay, so I think that we are getting.
But we
short.
started 5 minutes after. So.
Of course, yes. So let's go for the picture.
Ah, the picture.
Yes, the picture and then the coffee.
But the picture is outside.
In that order.